Hello, welcome back. This is 2.5. We're talking about infinite limits. These are limits that, with regards to the y, they just keep getting bigger, bigger, and bigger and bigger as they approach some x value, or lower and lower and lower and lower. So we're talking about going to infinity, which is kind of like going to the sky, and negative infinity, which is like going into the ground. Okay. So let's look at an example. From the book. So we have this really funny looking function, 2 times the absolute value of x all over x squared minus 4. Okay, we want to know what is the limit as x approaches -2 of f of x. Okay. Let's go into Desmos and see if we get a nice picture, because I'm curious as to what this thing looks like. I'm sure some of you are as well. Okay, so let's go search Desmos. And start graphing. And let's type this critter in and see what we get, right? So what was it? 2 times epsilon, if we do that for absolute value, right? X divided by x squared minus 4. Okay, so it's a sort of a lumpy looking thing. Let's zoom out a little bit. No, let's zoom back in. Okay, so as we approach -2, or even as we approach 2, from either direction, it looks like it's shooting up and up and up and up and up, right? So we can zoom out, and you see it just keeps on going up and 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 up. That's pretty crazy. Okay, zoom back in there. So it looks like it's going in either direction. It's going to positive infinity. Okay, so we would say the limit of f of x as x goes to -2 is going to be positive infinity. Okay, you could do a table of values and you would get the same sort of thing. So in your table of values, you just have to be a little careful about your approach. I always accidentally put in negative 1.9 coming in from the left. I mean to put in -2.1, right? So as we approach from the left, it'd be like that, -2.01 or whatever. And then, what happens exactly at -2. And then on the other side, that's the -1.9. Not really close to -1.99, 1.9. And if you put the numbers into your calculator, you get approximately 10, 100, and it just keeps getting bigger and bigger. And in this direction, you'd be getting like 999.7 something. This would be 99 something. So yeah, the numbers are getting bigger and bigger and bigger. Let's see what happens if we drop the absolute value, right? Let's experiment a little bit like we're scientists. Okay, so in this case, you see there's kind of, in one direction it goes to positive infinity, and the other direction it's going to negative infinity. In those cases, we can't really put a value on our limit. So for example, then if we had f of x where we drop the absolute value, just had 2 times x over x squared minus 4, for the limit as x approaches -2, we would just have to say it does not exist, okay, of this f of x thing. Of course, we could consider the different approaches, right? So as x goes to -2 from maybe the left of f of x, and the limit as x goes to -2 from the right of f of x. We could figure that out, right? Let me see, from the left, and we're thinking about -2, right? So from the left, it goes to negative infinity. From the right, it's going to positive infinity. Okay, so from the left, negative infinity. From the right, positive infinity. Okay. Regardless, it is a kind of non-existence, but we never, ever, ever write non-existent. If you write do not exist, I'm just going to assume you don't know what you're doing on a test. You have to put that infinity symbol there, unless it came in 2 different directions, and then yes, you would have to put the does not exist. All right. Anyways, we have a strict definition for the infinite limit, just like we had a strict definition for the regular limit. I will not be beating this to death. I'm not going to make us do proofs with these. But I just want to note it for the sake of completeness. So definition of an infinite limit And so we have f on defined on some open interval. So let f be a function defined on every real, or maybe I should say at every real number in some open interval containing this value we're approaching. Before it was -2, so we'll just call it C, containing C, and maybe it won't be defined at C. So in the previous example, it was there's an asymptote there. So containing C, except it might not be defined. So we'll say except possibly at C. Then this limit thingamajig, this notation, or the statement, limit as x approaches C of f of x equals infinity means that for any m value, any big M, like a million, a billion, Google million, any m greater than 0 that you could think of, there exists delta greater than 0 such that if we're within that delta distance, f of x will be bigger than that m value you provided. So such that if we are within this delta distance away from C, then the f of x value will exceed the m value that you provided. Okay, and then the negative version is just so for any m less than 0, there exists a delta such that if you get close enough to C, then your f of x you can find a delta such that if you're within that delta of C, then your f of x is less than the provided n value, which is the n being less than 0. Okay. So let's look at maybe another one. Well, no, I think we're good. There's a theorem in the book on vertical asymptotes, and I just want to note that fairly quickly. Let me get my book out. I hate my book because it's loose leaf, and it is not aging well. Okay. So let me look it up really quick. Maybe I should pause my lecture. Okay, so they give us some official vertical asymptotes, vertical asymptote definitions in the book. So maybe we can just put this in as kind of a star, a vertical asymptote. Because this is where generally where you have a limit going to infinity, it's going to probably happen at a vertical asymptote. So the first definition they give you is kind of a general definition. It says if f of x approaches infinity as x approaches C from the right or the left, then the line x equals C is a vertical asymptote. So how can I write that? If f of x goes to plus or minus infinity as x approaches C from either direction. So let me cheat a little bit and just put in the exponent of plus or minus, right? So always looking ways to abbreviate things. As x approaches C from the left or right, then the vertical line x equals C will be called an asymptote. Is a vertical asymptote. Okay. So things like the natural log will have a vertical asymptote because as you approach, so you know, what's the picture of a natural log look like? Looks like this. So as you approach from the right, the limit of the natural log, so I'm approaching from the right, that's a plus, is negative infinity. So therefore there is a vertical asymptote at 0 on the natural log, which maybe you're not familiar with. Okay, what else? If you're working with the rational functions, then on top of this, so vertical asymptotes and rational functions, where rational functions are ratios of polynomials, right? So for rational functions, you'll have an asymptote if that denominator is equal to 0, but the numerator is not. Rational functions, we have asymptote when numerator is not 0, but the denominator is. Okay, in general, that kind of also holds. The only requirement is the issue of continuity. So for a rational function, because the numerator and denominator are always polynomials, they'll always be continuous. But in general, you can say that's true for any sort of ratio of continuous functions. So that's theorem 2.14, which is a more general version of the fact about rational functions, right? So let f and g be continuous on some open interval containing C, and such that g of x is not equal to 0 for x not equal to C in that interval, then the graph of this ratio of the functions will have an asymptote there at x equals C. Okay, so it's a more generalized version of the rational functions that you probably saw in pre-calc. Okay, anyways, they'll probably throw some vertical asymptote problems at you. I'm not sure if they do in the homework, but it seems like they did. So find any vertical asymptotes, basically. So let's look at the first example. We have f of x equals 2 all over x minus 3 squared. So in this case, you're just taking the denominator and setting it equal to 0. It's basically looking for the non-removable discontinuities. You could think of it that way in this context. So you take the square root of both sides, and then we get a vertical asymptote at 3. Okay. Let's look at another one. G of x equals x cubed minus 8 all over x minus 2. So you may jump into this and say, ooh, it's 2. The answer's 2. And go on to the next problem. No, not so fast, buddy. Let's see. So same, opposite, always positive. So x squared, 2x, and then 4. All over x minus 2. So that x minus 2, because if you plug 2 into this equation, you would get 0 in the numerator and the denominator, and that's kind of not covered in our definition, right? So, and in our example, we need 0, the numerator not equal to 0, but the denominator equal to 0. So in this case, there's no asymptote. There'll just be a hole in the graph. Okay, great. Finding one-sided limits. So these are kind of fun once you get the hang of it. Well, the infinite types is what I'm kind of looking at here. And the first thing to note is that if you have the limit of a function f of x as x approaches c, and you plug stuff in and you get a number up top and a 0 in the denominator, it's going to be either plus or minus infinity. Okay? To figure out which one it is, all you have to do is a test value. Okay? So automatically, if you have something like this example, the limit as x goes to 1 from the left of negative 1 all over x minus 1 squared. When you plug in 1 to this expression, so taking the 1 from this part right here, if you plug 1 in, what do you get? Well, you get negative 1 in the numerator. And then in the denominator, you'll get 1 minus 1, which is 0, and 0 squared is 0. Okay, so automatically you know it's either going to be plus or minus infinity. The problem is figuring out which. Okay, so what I suggest you do is kind of do a number line for figuring out your approach. So I'm coming in from this direction. And then do a table, just 1 point table. It's like a test value. Okay. So you pick a value that's coming, that's approaching 1 from the left. So you're picking something like 0.9, and then you plug that into the function that we're working with, right? So you're plugging it into this thing that I just boxed in red. So all I need is a sign. I don't care about anything else, and the sign is going to tell me what type of infinity I have. Okay, so if you look at the thing in the box, in the numerator it's negative, and the denominator, if you put in 0.9, you'll get 0.9 minus 1, which is a negative, but you're squaring it, and anything squared is positive. So you get a negative over a positive, which is negative. A negative divided by a positive is negative. So that automatically tells me it must be the negative version, negative infinity. Okay. Okay. Let's look at some more of these. So the limit as x approaches 2 from the right of x over x minus 2. Okay, okay, so again, if you plug in 2, you'll get 2 over 0. So you know it's either positive or negative infinity. So I'm going to do my number line. I'm approaching from the right. Okay. So I'm thinking numbers like 2.1, and so I'll do a test value, 2.1. In the numerator, I have a positive, and the denominator, 2.1 minus 2 is 0.1, it's positive. So I'm going to end up with positive infinity. Okay? And you can carry on, you can make up your own examples. This doesn't take any sort of special talent. X going to negative 3 from the left of let's say negative x all over, I don't know, 3 plus x, right? Okay, so this time I'm approaching negative 3 from the left, okay? And then I do my test value. Well, I need the check to make sure it's not just a substitution, right? So if you plug in negative 3, you'll get positive 3. Down below, if you plug in negative 3, you get 0. So yeah, it's either positive or negative infinity. So in the numerator, I'm thinking numbers like negative 3.1. Or sorry, in the x values that I'm plugging in. Because I'm coming in from the left, I'm thinking things like negative 3.1, right? If I came in from the right, it'd be stuff like negative 2.9. Right, so if you plug negative 3.1 into the function, you get negative 3.1, which is positive, all over 3 minus 3.1, which will be a negative. So positive divided by negative is negative, and then we have infinity. Okay, let's do one more. So the limit as x approaches, let's say, negative 2 from the right, and let's try, I don't know, you can try anything you want, you know. Negative I don't know, x squared all over x plus 2. Okay. Okay, so let's make sure it's one of these forms. If you plug in -2, it's a negative parentheses -2 squared, which should be a negative 4. Downstairs, I have -2 plus 2, which will be 0. So yeah, it's one of these forms. All I have to do is figure out the sign. So I'm coming into -2 from the right. Oops, wrong. Well, yeah, I'm right. It's coming in from the right. It's real easy to screw it up, you know. From the right. And then do my little table. Okay. So I'm thinking numbers like -1.9. If you plug in -1.9 into the numerator, negative parentheses -1.9 squared is negative of something positive, which will be negative, and the denominator, -1.9 plus 2, is positive. So again, you're going to get a negative infinity. Okay, so we kind of are seeing we have these different types of forms. Before we had 0 over 0, which was kind of a, what do we call that, indeterminate. Now we have L over 0. Okay, we could figure those out. Those are always plus or minus infinity. There's other types, though, and the book introduces these as the infinite limit laws. And you have to kind of you're going to have to try to extrapolate some of the laws from what they give you, because what they give you is not by any means complete. So first note that L is assumed to be positive. Okay, L is greater than 0 for these examples, I believe. Okay, so if you have the limit as x goes to c of f of x plus or minus g of x, the form is infinity plus or minus L. Okay, and the infinity will completely dominate the L. If you think of a table of values, it'll be like 101, 1001, 10,001, 100,001. It's just going to infinity, and plussing on or minusing on one number is unaffected. So if you subtracted one away from something going to infinity, it'd be like 99, 999, 9,999. It's going to infinity. Okay. Likewise, if you go in kind of the opposite order, although it doesn't say it in the book, if you go L minus infinity, in our sort of terms, it would be thinking g of x minus f of x. That's going to be the form L minus infinity, and in that case, minus infinity will be the dominating term. If you go limit as x goes to c of g of x plus f of x, that's going to be L plus infinity, and regardless, even if L is less than 0, it's still going to be infinity. Okay, so adding a constant into something that's just getting bigger and bigger and bigger, so long as the constant's always the same, won't affect the fact that it's always going to get bigger and bigger and bigger. Okay. Some other factoids, like number 4, the limit as x goes to c of f of x times g of x, okay, which is like infinity times L. You can multiply these out. It's just going to be infinity. Okay? If one of those factors are negative, so for example, if I introduce a negative on the f of x and then times g of x, where L is greater than 0, that'll be negative infinity times L. And at the end, it's like a negative times a positive, so it ends up being negative infinity. Okay? When you're doing division, so if you have something like L over infinity, limit as x goes to c of g of x over f of x, which I'm calling L over infinity, unlike L over 0, it will go to 0. Okay. Okay, so just to kind of sum it up in terms of all these L's and infinity symbols, let me sort of give it to you. So let's say first L is greater than 0. Okay, so L times infinity will be infinity. L times negative infinity will be negative infinity, or vice versa. Okay, so that's also the same as infinity times L, which is negative infinity times L. L plus infinity is going to be infinity. L minus infinity is going to be minus infinity. Infinity minus L is going to be infinity, negative infinity, and this will be plus or minus L. Negative infinity plus or minus L will be negative infinity. Okay. And hopefully you're kind of figuring out, how it's going to work, right? So let's try the L less than zeros. L times infinity will be negative infinity. L times negative infinity would end up being positive infinity. It's like a negative times a negative is positive. It's that idea. L plus infinity will be infinity. L minus infinity is negative infinity. Infinity plus or minus L will still be infinity. And negative infinity plus or minus L will still be negative infinity. And then for multiplications of two infinity types. So if you have infinity times infinity, for example, something like the limit as, I don't know, x goes to 0 from the right of x, let's say 1 over x, sorry. 1 over x times ln of x. Okay, so if you look at the graphs of those as x goes to 0 from the right, 1 over x is going to infinity. And so this isn't exactly the same. This will go to negative infinity, right? In that case, you'll have an infinity times negative infinity, which will be negative infinity. Okay, so what I'm saying is at the end of the day, maybe a better example, limit as, I don't know, x goes to 0 of 1 over x times 1 over x squared, right? Maybe something like that. This will be infinity. This will be infinity if I come in from the right. And infinity times infinity will just be infinity. Okay, so this will be infinity. Infinity times negative infinity will be negative infinity. Negative infinity times infinity will be negative infinity. Negative infinity times negative infinity will be infinity. Just keeps saying infinity plus infinity will be infinity. Negative infinity minus infinity will be minus infinity. The only ones you really have to watch out for are when you have kind of competing interests. So warning. You still have these indeterminate forms floating about that we'll see in Calc 2 usually. Sometimes you see them in Calc 1. But the indeterminate types, right? 0 over 0, infinity over infinities. What was the other one? Infinity minus infinity, negative infinity plus infinity, and some of these weird ones where you have something like infinity to the 0 power. These guys are indeterminate. We don't, except for the first one, we don't really know how to deal with them yet. Okay, so these are indeterminate. And you can see some of them look a lot like determinate forms, like the infinity minus infinity looks a lot like infinity plus infinity. But the idea is that there's a competition. Like one is getting really, really big and the other one's going in the other direction, so maybe they cancel each other out, right? That's not always going to be the case. Infinity minus infinity does not necessarily equal 0. Okay? Okay, let's look at maybe one or two more from the book. And here we go. Example, limit as x goes to 0 from the right of 6 minus 1 over x cubed. Okay, so this is the form L minus some sort of infinity, or maybe it's L plus infinity, right? I just have to figure out what kind of infinity I'm dealing with. So in particular, I'm taking a look at the 1 over x cubed as x goes to 0 from the right. So I have 0, I'm coming in from the right. So my test value, I'll pick 0.1. So I'll have a positive over a positive, which is positive. Okay? So this is L minus infinity, and from above, that's minus infinity. Okay? Let's look at another example. The limit as x approaches negative 4 from the left of x squared plus 2 all over x plus 4. Okay. So again, the issue here is with that second part. So it's L plus or maybe minus infinity. I don't know. So I have to look at the limit as x goes to negative 4 from the left of this 2 over x plus 4. Okay, so I'm approaching negative 4 from the left. So I have xy. So this is negative 4.1-ish. And you'll have a positive over a negative. So this will be negative infinity. In other words, this is L minus infinity, which is minus infinity. Okay, for ones that are type L over 0, but they're not kind of this polynomial, you still do the same approach, except maybe you use a graph to kind of do your test value. Okay. So the limit as x goes to pi over 2 from the right of negative 2 all over cosine x. Okay, what is that? If you look at the graph, you can pick out your test values. Okay, so cosine looks like this. Exactly at pi over 2, cosine is 0. Okay, so it is an L over 0, so you know it's either going to positive or negative infinity. If you take an open interval around pi over 2 and you're approaching from the right, the corresponding y values are positive or are they negative? They are negative, right? So for your test value, as we approach from the right, you're getting something bigger than pi over 2 for your x value. I don't know, I'm just kind of guessing. So I'll say pi over 2 plus something, right? So our output in that case in this function above that I just put in a white box will be negative 2 all over. So what is cosine as we approach from the right? Cosine I just found is negative, right? So for this little dot here, as I approach from the right, the cosine values, the corresponding y values will be negative. Okay, so the denominator will also be negative. So a negative over a negative is positive. Okay, okay. So hopefully that will get you through the homework and that sort of stuff. You use limits an awful lot, so please don't blow them off. This is fundamental to your education and calculus. It's really the first calculus type topic that we've covered so far, and we use it significantly in math. So please do your homework and, okay, so I'll leave it at that, and I'll see you next time. Okay.